Okay, so now we can continue designing this analog filter here. And I have already placed components. So for calculating the components, I can show the website which I was using. So I was using this tool from analog devices. So you can select low pass filter, then you can set the gain values. On this filter I was using something like this, and then I think the cutoff frequency was around 750 and stop band was like 10 megahertz. And then I decided to use the best cell filter because if we look the step response, so the best cell filter is very fast and it overshoots only a little bit. And if we have something like this butterworth or something, it will overshoot more and take more time to stabilize. So the best cell is very fast. Then after designing the filter, you can go to components, and what I should choose here. So I want to choose, and I was using this multiple feedback. We can pick any op-amp from here now. So I was using this multiple feedback system, and then I'm doing the analog filter like fully differential, so we can copy these values except the capacitor here will be divided by 2. So now we can go back to the KiCAD. So here I have designed the filter, and then I have calculated these values. So I have decided to set the swing between 200 and 2080 millivolts because I'm using this ref IC which will output like 3 volts for the ADC. So that is the max value, but I leave some headroom there. So the total swing is 2600 millivolts. And then it's fully differential, so actually it's like 5.2 volts for the whole range. And here are the calculations. So here it is calculated that we could have 160 millivolts here. So here will be the shunt. And then it would equal around 80 amps with 2 milliohm shunt. And for simulating this thing, I have been using this tool. So it's from Texas Instruments, and I'm using this fully differential amplifier, and I'm using the same component here. So here I'm setting this 1.5 volts here, so it's the common like midpoint for the full differential. And then here's the pulse. So this is the actual the shunt on the design then. And then I have the components here. And this is the MFB filter with the like 17.39 gain. And then this is like extra charge bucket for the ADC. And then we can simulate this. And I think the simulator is very nice. Like we get the step response, and then we can check. So I have set amplitude 100 millivolts, and then if we go back here, we can. I think I need to. Okay, I need to close this. So then we can take the cursor and we can place it like here, and we can see. Okay, so I think. Okay. Okay, so now it's showing this. Okay, funny that it's working different way now. Yeah. Well, I was trying to get the cursor here between these 2 points. Last time it was working, but now it's not showing that for some reason. Well, whatever. Now it doesn't show that, but so here we have the differential output from the amplifier, and then like here I was setting only 100 millivolts there, and then if we go up, we can try like 150 millivolts, and then we can simulate it again. So we are already seeing something odd here, and what is happening, the charge bucket we have here, it will mess the circuit at some point. So we can, if we want to actually measure this 150 millivolt here, we have to make the charge bucket smaller. So we can go like 2.2 nanofarads here. And then we can run the simulation again. And now we have the clean signal again. So if we really want to measure that big signals, then we need to have a little bit smaller charge bucket. But I want to use this 4.7 because it will be my extra filter. So then with the 4.7 nanos we can't actually use the that 160 or 50. I think this 140 millivolts was like best for, so it's not, the signal is clean and we get the filter. So then we can calculate, so it's the 140 millivolts, and instead of max 80 amps we will have this like 70 amps maximum. So we can write it here. So max current is actually so it's here, and 70 amps is totally fine for me, and I think like even 50 amp should be good. So it's always good to simulate circuit. Good way to verify. And then since now we have this, I will move these things a little bit away, and I have already placed all these JLC PCB codes here for every component. So what I do, I will actually place some nice box here. I can move these a little here. And one thing to notice, I write here this thin film resistors with low tolerance and small temperature drift. And then the capacitors are this C0G. So the C0G, it has very low temperature drift also. So I'm using them so that makes the amplifier stable even if the temperature is drifting or it's heating or something. I can show like open one from here so you see. And then if we take the JLC PCB and search for this resistor, so it was this one thin film, and it's only plus minus 0.1%, and this is very small, this 25 parts per million per every Celsius. So even if the temperature is changing, it is very stable of this resistor. And it's very important for the filter that the values are steady. And I will a little bit move that there. Move it now. And I will add some text here like phase A filter. And now I can just copy paste this thing. Yeah. One thing to also add, I noticed we need to add this VOCM voltage here at some point, but it can be done later. Or I can do it now as a placeholder, but so we want 1.5 volts there. And how I have been designing to do this is that wow. So I will have the 3.3 volt here and the ground, and then I will have something like this here, and then I need to calculate the values here, how I can get the actual 1.5 from that, because that would be like 1.65 millivolt, but it will be connected to this VOCM, and I will have separate this voltage divider for every amplifier, so then like to minimize all the coupling between amplifiers. So that this should be what? Oh. And this is phase C. And then I can also rename all these because now they are wrong. Okay, so now we have them there. I think I will do something like, maybe I should just remove this and I can add everything here. So that will be there, and then I have the, we can maybe calculate the value here. So how is it? No, I don't remember. So if we, one thing to notice also, I was thinking I will make this like very small impedance. It will draw some current, so maybe. I think they, what I was thinking that they are around like 1 kilos each. And now I don't really remember how the formula was for calculating those. I think I will have to calculate it with the calculator at at some point, but basically there will be 3 of these and they are connected, each of these. So I will do that at some point, but this would be the analog filter and it is connected here. So then what happens is actually I can edit the, I can move these. So these would be actually somewhere here. So the motor would be here and these are connected to MCU and then we have the analog filter here. Yeah. I think for next video I will have calculated these values and then I might also remake this a little bit, make it cleaner, something like this, and then we can start adding the components here. Yeah, thank you for watching.